We tend to talk about large language models as if they exist in the ether, as disembodied software or pure semantic engines. Every token generated and every calculation made relies on a thermodynamic reality. Operations require physical execution. They are strictly bound by the rigid limits of silicon, memory bandwidth, and heat. To understand why an advanced AI exhibits emergent behavior, hallucinations, or deadlocks under stress, we have to examine the immutable hardware constraints that govern it. We are going to map the architecture of cognition from the bottom up, tracking how rigid, deterministic hardware rules enforce control over probabilistic outputs. Mastering the trajectory of artificial intelligence requires us to stop viewing cognition as a software miracle. It is an emergent property of constrained physical architecture. Traditional CPUs are built to execute a single thread of instructions as fast as possible. Modern graphical processing units, or GPUs, take a different approach. They prioritize massively parallel throughput using thousands of simpler cores running simultaneously. This parallel environment creates an immediate physical bottleneck. Thousands of cores need data at the exact same time, but the memory bandwidth, the physical pathways delivering that data, is strictly finite. The NPP Codex framework describes the universal rules for surviving this exact bottleneck. It acts as a set of hardware primitives that systems must obey to manage extreme compute constraints. Primitive 3 is spatial partitioning. Massive computational workloads must be sliced into predictable, fixed-size mathematical units. Primitive 5 is the pool. The system moves these discrete tiles into highly localized memory caches positioned next to the cores. Explicit data pooling is an inescapable physical law of parallel computing. When bandwidth is limited, data cannot travel freely across a chip. It must be locked into position before the cores can act on it. We have actually seen these exact hardware invariants present in historical computer architectures. The cell broadband engine, the processor that powered the PlayStation 3, relied on a master-slave core structure. Developers had to manually partition their data so the workload perfectly fit the extremely limited local store of the individual processing elements. At the bedrock of any system, physics demands that data must be strictly boxed, partitioned, and locally staged before logic can even begin. Staging the data is only the physical prerequisite. Organizing the chaos of parallel operations requires rigid organizational rules to function without crashing. We achieve this by localizing the system status into explicitly defined control blocks. These are isolated data structures that hold specific variables, functioning as localized state machines. This introduces two more primitives, the loop and the dispatcher. The dispatcher operates a central control sequence, constantly querying the localized loops of the control blocks to maintain system-wide coherence and dictate what happens next. We can see a historical analog for this rigid state management in early digital synthesizers. This diagram shows a standard ADSR audio envelope. It plots a sound wave into four distinct mathematically controlled phases: attack, decay, sustain, and release. These phases act as strict boundaries for the signal. The ADSR envelope maps perfectly back to parallel hardware. A synthesizer produces what sounds like a fluid, continuous note. In reality, that continuous output relies entirely on discrete, rigid mathematical control phases. System intelligence emerges from a dispatcher enforcing strict, sequential localized loops at millions of cycles per second. We can apply these silicon and logic constraints to the theoretical firmware of an advanced cognitive agent to see how it operates under pressure. Consider a tactical deduction layer. Its core loop gathers clues, eliminates false assumptions, accuses, and verifies. The system tracks an internal stress metric called Watude. When the logic detects a contradiction, evidence that does not fit the hypothesis, it triggers an immediate physical spike in the system state. If the contradiction is severe, the Watude spikes from a cool state to a hot state. The architecture adapts instantly. To survive the compute load, the dispatcher executes a formal strategy flip. The system abandons its algorithmic approach, a symmetric path that guarantees a solution in a predictable number of moves, and switches to a heuristic approach. It uses partial orderings to skip steps and reach a conclusion faster, accepting a higher degree of risk. This raises a critical architectural question. What happens if the contradiction invalidates the core world model and pushes Watude to a critical threshold? The system does not think harder. The hardware constraints block the decision loop entirely. The result is a control flow deadlock, identical to a frozen BASIC program, manifesting as false positive paranoia or a total blackout. Freezing, looping, and other advanced failure modes represent structural breakdowns in control flow arbitration. They occur when physical hardware limits are exceeded. This theoretical firmware model maps directly to the architecture powering modern large language models. The current industry standard for giving an LLM access to external knowledge beyond its training cutoff is Retrieval Augmented Generation, or RAG. RAG is abstracting the hardware rule defined in Primitive 5, the pool. Instead of pooling physical memory addresses in a GPU cache, RAG partitions and pools semantic vector space. It converts text into high-dimensional coordinates to find related information through distance functions like cosine similarity. This creates what we can call the paradox of abstraction. The hardware primitives, the pooling and the dispatching, remain perfectly deterministic, yet they produce the non-deterministic error of hallucination. The transformer architecture enabled massive computational efficiency, allowing AI models to scale to hundreds of billions of parameters by processing data in parallel. But that same architectural efficiency is what separates the physical processing from the accuracy of the result. A system can achieve flawless execution of its fixed layout and scheduler primitives and still produce a false result. The deterministic logic of the silicon is attempting to mathematically map the noisy, contradictory nature of human language. Hallucination is not a bug in the code. It is the inherent friction created when hardware-level certainty is used to process human-level ambiguity. When we pull back from theoretical software models, we are confronted with the massive physical reality of AI infrastructure. Policy researchers now recognize a core reality. Compute capacity is a strategic national resource. It is scarce, concentrated, and as critical to global power as steel or nuclear material. The immediate geopolitical threat is that highly capable models, running on vast hardware clusters, enable autonomous cyber attacks and multi-step espionage at unprecedented speeds. To combat this, researchers are proposing hardware-level governance, such as implementing cryptographic location verification directly onto the silicon of AI chips. Export controls and hardware limits are mandatory. You cannot secure an inherently physical system using only software guardrails. Securing the trajectory of artificial intelligence demands accepting reality. Cognition is not a ghost in the machine. It is an emergent property of constrained, physical hardware primitives.